Hello everybody. So in this video we're going to talk about amplifier design. So we will start from simple specifications and design everything from scratch including the biasing circuits. Okay. So alright, so this is what we're given. We want to make an amplifier with a gain of 50, or this is the open circuit voltage gain of 50. Okay. And then we are given a MOSFET. Right. So when we have a MOSFET, there are two important characteristics which we need for our calculations, or two important properties of the MOSFET. One is the transconductance parameter, which is given as 10 milliamps per volt squared, and the two, we need the threshold voltage. And the threshold voltage is given as 2 volts. Right. So that's one. So we have one MOSFET. We need a gain of 50. There's a power supply of 10 volts. Power supply. And then so these are what's given to us, and we can use resistors and capacitors, etc. But these are the main. So we need a gain of 50. We have one MOSFET. We have a 10 volts power supply. All right. Okay. So since we need a gain of 50, so I'm going to go with a common source amplifier. Okay. So at the most basic level, a common source amplifier looks like this, where I have RD. And then this is usually a power supply, and then an AC analysis that becomes ground. The source is grounded. I'm applying the input here. Okay, and then my gain GM is so gain AO is equal to negative GMRD. All right, and then we'll just assume that this 50 is just the magnitude, so minus 50 is also fine. All right, so that means we want GMRD to be equal to 50. Right. Okay. So now there is a simple way of calculating RD, and we may get to that later. So at this point, let's take RD to be, let's say, 35 kilo ohms. Okay. And then this choice is it's not very fixed. I mean, we have a lot of flexibility in choosing RD, and I chose 35 kilo ohms, and maybe at the end maybe I'll talk about how to choose this too. So now let's say we know RD is 35 kilo ohm. Okay. So this implies my GM is 50 divided by RD, which will be equal to 50 divided by 35, 35 milliamp per volt. Okay, that would be the units of it. So this will be 10 over 7 milliamp per volt. Right. So if you refer back to the video where we actually derived GM, for small signal analysis, we find that GM will be equal to Kn times VOV. VOV is the overdrive voltage. Okay, so this will be equal to Kn times VGS. Now VGS is a DC voltage across the gate in the source, right? So if you look at in this circuit, we are not talking about DC voltages, but then VGS at the DC comes from the DC biasing circuit, and we'll talk about that later. So minus VTN, which is the threshold voltage. Okay, so that means my overdrive voltage will be equal to GM divided by Kn, okay, which will be equal to my GM is 10 over 7 milliamp per volt, and my Kn is 10 milliamp per volt squared. Okay, so this will come out to 1 over 7 volts. That's my overdrive voltage. Okay, so that means my DC VGS will be equal to overdrive voltage plus VTN, which will be equal to 1 over 7 plus 2, which will be approximately equal to 2.14 volts. Okay, so that's my gate to source voltage, the DC voltage. Now, all right. So now let's go to, so from my AC analysis, I figured out that my overdrive voltage should be 1 over 7 volts. That means my VGS should be 2.14 volts. Okay, so now I'll go back to my DC circuit and basically make sure that I set my VGS to be 2.14 volts. Okay, so now let's go to our DC circuit. I'm going to redraw the common source amplifiers first, just a small signal, and this time I'm going to draw the ground like this. And this is RT, and this is where I was applying my small signal VI, and this is the ground. Okay, so if you look at actually the DC complete circuit with the DC biasing, I can, for example, maybe use a voltage divider to set a particular voltage here. This is 10 volts, and then another resistance here, which is the ground, and then I'm going to superimpose my AC signal like this. Okay, so let's say this is R1, this is R2. Right, now if I ground this, if I ground the source, then all I have to make sure is I have to set R1 and R2 such that this voltage is equal to VGS, which is 2.14. Right, so that means if I make R2 small compared to R1 in such a ratio, I can choose the ratio to make this 2.14. Okay, but there's one thing we need to make sure or we need to observe is, if you're looking at the input impedance here, if this capacitance is large enough, then it's basically a short compared for the AC signals. Okay, and there is no current going in here, so the input impedance looking in here for the AC input impedance is basically R1 in parallel with R2. Remember, for AC analysis, we just ground the power supply, because as far as AC is concerned, my DC is just a ground, right? Because it's not changing, so no AC signal over there. So that means as long as my AC is concerned, R1 is in parallel with R2. So if I make one of them smaller, then the parallel resistance will be smaller than the smallest resistance. So it makes sense for me, in order to keep my input impedance high, to keep R1 and R2 equal and both high. Right? So that's what I'm going to do. Right? So I'm going to put 1 mega ohm here, which is very high, and another 1 mega ohm here, which is also high, so that my input impedance now is R1 parallel R2 is 500 kilo ohm, which is high, which is good because I want high input impedance. But that makes my DC voltage here 5 volts. Okay, so if I ground my source now, that means my VGS will be equal to 5 volts, but I want my VGS to be 2.14 volts. So what I'm going to do is I'm going to put a resistance here, RS, such that there will be a certain voltage drop here, and then I want the voltage drop here to be exactly equal to 2.86 volts. Okay, so now since I want VGS to be 2.14, if this is 2.186, then VGS is 2.14, right? So 5 minus 2.86 will be 2.14. Yeah, there you go. So if I make this 2.86, then my VGS is 2.14, which is what I want. Okay, but then this is no longer a common source configuration, right? Because for common source, I need my source to be grounded. So now the trick is, for the common source configuration, we have to notice that the source should be grounded for AC signals, right? So all we need to do is use a bypass capacitor, which is again a very high capacitance here. I'm writing infinity, but it's just a, for example, you can use 20 microfarad or 10 microfarad, which will be large for most of the interesting frequency signals. But let's just say infinite, so that it will definitely be a short for AC signals, right? So now, if you look at this circuit, for DC signals, this is open, and the resistance between source and the ground is RS. For AC signals, this capacitor is a short. Therefore, as long as AC is concerned, the source appears as if it is directly connected to ground. Okay, so that's how we're going to deal with that. So we're going to put an RS here. So we're using this RS to keep this, to compensate for the fact that this is 5 volts, and therefore we need my VGS to be 2.14 volts. And we are setting this to be 5 as a byproduct of making these resistances equal. Okay, and we are setting these resistances equal because we want high input impedance. All right. Okay, so we went all the way over there, and then we said, okay, this should be 2.86. Now, if this is 2.86, then how much should RS be? Right? If you want to calculate RS, we need to know how much current is going through the RS. All right. In order to do that, let's see. So now we already know this RD. We already selected it to be 35 kilo ohm. Okay, and that is how we calculated the VGS. We used 35 kilo ohm and said that VGS should be 2.14. Okay. Now, we also calculated our VOV to be 1.7 volts, right? Now, if we use our saturation equation, my ID is equal to half Kn VOV squared, okay? So that will be the current here, ID, the DC current. And the same current will also go through RS. So if we can find ID, then we know the current going through RS and we know the voltage drop across it. So we can find RS, right? So note that in here, we know Kn and we know VOV, so we can calculate ID. So let's do that. Half Kn will be 10 milliamp per volt squared times 1 over 7 squared. Okay, so this will be 10 and this is volt squared, right? So 10 divided by 2 times 49 times milliamps. Okay, this is ID. So 49 times 2 is approximately 100, 98 which is approximately 100, so this will be 0.1 milliamp. That's ID. Okay, so if this is 0.1 milliamp and I want a voltage drop of 2.86, that means my RS should be 28.6 kilo ohm. Okay, so that's it, right? So I know now I have the power supply of 10 and I know what these resistances are. This was I told we just took this for granted, or I gave you what this is. We did not actually calculate it. And then I know what RS is. So I know all the resistances here, and I know my gain now. If I, for AC purposes, gain, if I look at VO over VI, that will be equal to 50. Okay, so that's basically how we design all the DC biasing circuit and my gain of 50. Okay, so now let's look into how did we get 35. Okay, so before that, here I'm using a saturation equation, right? That means I'm assuming my MOSFET was in saturation. But we'll have to make sure that, once I calculate, I can calculate the voltage at every point in the circuit, and I can make sure that the MOSFET is actually in saturation, right? Okay, so in order to do that, I know VG is already 5 volts. And can I calculate VD? Yes, because I know the voltage here, I know the current through here. So my VD, the voltage at the drain, will be equal to VDD, which is my power supply basically, minus ID times RD, right? My VDD minus ID times RD will be VD. So this will be equal to 10 minus 0.1 milliamps times RD is 35 kilo ohm. So this will be 10 minus 3.5 volts. This will be equal to 6.5 volts. Okay, so my VD is 6.5 volts. All right, how do we check for saturation? For saturation, we need VDS to be greater than or equal to VGS minus VTN. Right, so this implies my VT minus VS should be greater than or equal to VG minus VS minus VTN. Cancel out these things. I want VD to be greater than or equal to VG minus VTN. All right, so my VG is 5 volts. Okay, so VG is 5 volts and VTN is 1.7 and VD is 6.5, right? So 5 minus 1.7 is obviously less than 5, so VD is definitely greater than VG minus VTN. That means my MOSFET is in saturation. So that means this equation is correct and everything checks out. Okay, so now to summarize, I calculated the values of all resistances except this one, but at least in the circuit I know the values of all the resistances, and I know the gain to be 50. Okay, so that means that completes the design, and I know that MOSFET is in saturation. That completes the design. Now let's see how to calculate RD to begin with, right? So okay, so here's how you do this. So we're going to say that, okay, so in order to keep the input impedance high, we are going to have these two resistances to be equal. That means we already know that this is going to be 5, okay, or this is going to be half that voltage. So now if we make sure that the drop across this resistance RD is 1/3 my power supply, so here the drop across this resistance is half. If I make sure the drop across this resistance is 1/3, then I'll definitely make sure that my drain will be at a higher potential than my gate, right? So then what I want is my voltage drop across RD to be 1/3 my power supply, okay? So now, all right, so I know my gain to be equal to GM RD, right? And let's see, GM is equal to KN VOV, right? So that means GM squared over 2KN is equal to ID, right? I want you to pause the video here and make sure that this is actually true. So this implies in saturation, GM is equal to square root 2KN ID, right? So that means my gain is equal to, my gain is equal to square root 2KN ID times RD, all right? So this implies ID is equal to 1 over 2KN G over RD squared. All right. So now I said I want the voltage drop across this resistance to be 1/3 the power supply, right? And the voltage drop across that resistance is ID times RD. So I want ID times RD is 1/3 the power supply VDD, right? So this implies I'm going to substitute ID from here. So this implies 1/3 VDD is equal to 1 over 2KN G over RD squared times RD. So this is equal to 1 over 2KN RD times G squared is 1/3 VDD, right? So that means my VDD should be, also my RD should be equal to 3 over 2KN G squared over VDD, right? And if you substitute all these values, this will be 3 times 25 squared divided by 2 10 milliamp per volt squared times 10, and this will come out to be approximately, let's see, approximately 37.5 kilo ohm, right? And I just chose 35 kilo ohm to be round off, okay, and to make our calculations easier at the time. So that's how you can calculate RD. All right, so that's basically completes the design. So let me summarize this. So what we were given at the beginning is a gain of 50. That's what we wanted to make. We wanted to make an amplifier of gain 50. We had one MOSFET which had these KN and VTN, and we had one power supply of 10 volts. Okay, so we said, okay, we're going to use common source amplifier, and a common source configuration small signal analysis looks like this, RD. And I determined RD using this calculations which we just went through, and then we determined RD to be close to 35 kilo ohm. We went back here And we said GMRD should be 50, and then since we know what RD is, we calculated what GM was. From GN, we know what VOV is, and that turned out to be 1.7 volts. And if we know the overdrive voltage VOV, then we know VGS, because VGS is nothing but VOV plus VTN. So that came out to be 2.14 volts. All right. So then we went back to our DC biasing circuit. We know that these two resistance have to be equal, so this has to be 5. So if this is 5, we know this has to be 2.86 because VGS should be 2.14. If this is 2.86, we calculated the current through the drain and the source, and then from that current we calculated what RS was. Okay, so then once we calculate RS, we know everything in the circuit, and we also just proof checked to see if the MOSFET was actually in saturation, and it turned out to be it was. I mean, it has to be, right, because that's how we designed our resistance to begin with. Okay, so that's basically amplifier design.